So in this video we're going to go over how to develop the formula for a second solution using reduction of order. So the first two videos we showed examples of working through the reduction of order process for specific second order linear homogeneous differential equations. What we want to do now is look at the general case, show that we can come up with a formula. In the homework you aren't allowed to use the formula, but in later assignments we'll need this. So this will be a tool that we'll use moving forward. So the idea is, if we have a generic second order linear differential equation that's homogeneous, if we remember from the previous homework and the set of videos that went with that, we can't have a sub 2 being equal to 0. And because this coefficient on the y double prime term can't be 0, it's okay to divide everything by a sub 2. And if we do that, then we'll wind up with a coefficient of 1 on the second derivative term. And then what we can do is just recognize a sub 1 over a sub 2 is just a function of x, and a naught over a sub 2 is just a function of x. So let's just give them names. Let's call this guy P, and we'll call this guy Q. So Q is those two ratios that we had there. So that's step one. Now we have a homogeneous equation, linear second order, leading coefficient of 1 on the y double prime term. And remember, the premise is that we need to know a solution y sub 1. We have to be able to find a solution. And when we find a solution, we guess that another solution exists and has the form u times y sub 1, where u is just some function of x. And then what we've been doing in the first two videos is we differentiate this. We take the first derivative and the second derivative, and we plug the results in, and we hope that good things happen. That's kind of how the game plays out. So we take the first derivative, which is going to look like u prime times y sub 1 plus u times y sub 1 prime. And then we need to take the second derivative, so we'll need to apply the product rule to each of those two terms. So the second derivative is going to be u double prime y sub 1, and then u prime times, so plus u prime times y sub 1 prime. Now we take the derivative using the product rule of this guy. We get plus u prime times y sub 1 prime. And then we see that we're actually getting the same thing twice. So we can really just say plus 2 times u prime y sub 1 prime plus u times y sub 1 double prime. And now we're going to take y double prime, y prime, and y and plug them into the homogeneous differential equation. But we want to do it in a very specific way. We need the linear terms to cancel. So we group those linear terms together as we plug things in. So when I plug y double prime in here, I'm going to get a u double prime times y sub 1 plus, I'm going to get 2 u prime y sub 1 prime plus, and I'm going to tuck them over here, plus we're going to get the u y sub 1 double prime. Now we do p times this, so we're going to get plus p times u prime y sub 1 plus we're going to get p, right here, p times u y sub 1 prime, and then finally q times u y sub 1, so plus a q times the u y sub 1 right here. And what we want to notice is that the u shows up in all three of those because of how we grouped them. So we can actually factor the u out. So I'm going to factor that u out. And when we do that, well, we want to notice what we have here, this y1 double prime plus p y sub 1 prime plus q y sub 1. This has to equal 0. Y sub 1 is a solution for the differential equation. So when we replace y with y sub 1, y prime with y sub 1 prime, and y double prime with y sub 1 double prime, it needs to equal 0 or it violates the premise that y sub 1 is a solution. So this whole piece that's times the linear term u winds up canceling. And we get just this equal to 0. And that was the key of how, in the first two videos, that was the key to how things were working out, that u to the first power term always canceled. And now the u prime shows up here, so we can factor a u prime off. So we get 2 y sub 1 prime plus p times y sub 1, and this is times u, and this equals 0. And then we have a u double prime y sub 1 here, and I want to, and plus, and then I can divide everything by y sub 1. So if I divide everything by y sub 1, I'm going to get this over y sub 1. And this is a u prime term right here. And I can actually bring this up into each of the two numerators, so I wind up getting a u double prime plus parentheses 2 times y sub 1 prime over y sub 1 plus a p, because y sub 1 divided by y sub 1 is just 1, and this is a u prime. And then what I'm going to do is I'm going to do a couple things here. One, I'm going to make that substitution now. I'm going to recognize that this is really a first order equation because I have a function u prime and its derivative here. So this is where we made that substitution before, w equals u prime, which meant w prime equaled u double prime. So we'll substitute and replace the u prime with w. You can do it without doing this, but it does help you see that it's a first order equation here, and it's actually separable because this w prime is just dw dx. And then if I subtract this term from both sides, I won't have a 0 over here anymore. I'll have the opposite of 2 times y sub 1 prime over y sub 1 plus a p. And that's times a w. That's by subtracting the w from both sides. Multiply both sides by the dx. Multiply both sides by 1 over w. And I wind up with 1 over w dw. And this stuff here is all dx stuff. And thus we integrate. And when we integrate, we get a constant of integration. And what we want to notice is here we're just going to get the natural log of the absolute value of w minus, right here I'm actually going to get, I'll put it in parentheses for now, I'm going to get 2 times the natural log of y sub 1. Remember, the derivative of the natural log is 1 over the stuff, so we get 1 over y sub 1, and then you have to multiply by the chain rule by the derivative of the stuff. So anytime we have that form crap prime over crap, when we integrate it, we get the natural log of crap. And here, plus, I don't know what the function p is, so I'm not going to be able to integrate that. But I'm going to have my constant of integration. I'm going to move this natural log of w a little bit. Natural log of w. We'll give ourselves some space. Distribute the minus sign into the two terms. So the minus is going to go here. I'll get minus 2, and that minus will change this to a minus. Now I can add this to both sides, so I get plus 2 times the natural log of y sub 1 equals the opposite of the antiderivative of p dx. And then exponent rules, I can bring this 2 up into the exponent position inside the logarithm. So I get the natural log of y sub 1 squared. And I have the sum of logarithms now, which can be replaced with the logarithm of the product of the inside functions. That's just using our log rules. So we get this mess right here. So p dx plus our constant of integration. We'll exponentiate both sides base e to get the stuff inside the natural logarithm out. So I'm going to be left with w times y sub 1 squared equaling e to the negative antiderivative of p dx plus c. But I have the sum of two elements in the exponent position, so I can break this up into times e to the c. And e to the c is just a constant. We'll name him c sub 1. Once I do that, I can divide both sides by y sub 1 squared. So I'm going to slide up here. So when I divide both sides by y sub 1 squared, I've got c sub 1 over the y sub 1 squared times the e to the opposite of the antiderivative of p dx. But w, we made the substitution right here. W is just u prime. So we replace w with u prime. And to find out what u is, we have to integrate both sides with respect to x. And we'll have to add on another constant of integration. So when we're done, let me give myself some space down here. When we integrate this, we integrate u prime, we get u equals. This constant can factor out front, so we have c sub 1 times the antiderivative of e to the opposite of the antiderivative of p dx, where that p is just coming from right here. And then it's dx plus our c sub 2, and this is what u is. Remember, we hypothesized that we have another solution of the form u times y sub 1. So to find out what y is, our hypothesized solution, we have to multiply u, which is this stuff here, by y sub 1. And then we distribute that y sub 1 into the parentheses. So I'm going to get c sub 1 times y sub 1, c sub 2 times y sub 2. So here's our first solution, the way that it played out when we did worked examples in the first two videos. And c sub 1 can be anything, so I let it be equal to 1. And what we wind up with is here is another solution. I lost my y sub 1 squared right here. It needs to come down underneath that e. I pulled the c sub 1 out, and the e should be in the numerator over this y sub 1 squared term. So I get this. So it turns out that here is our second solution, y sub 2. So y sub 2, our second solution, is just going to equal y sub 1 times the antiderivative of e to the opposite of p dx all over the y sub 1 squared dx. And then our general solution is just going to be c sub 1 times y2 plus c sub 2 times our y1. I should actually keep this consistent. It should be c sub 1 y sub 1 and c sub 2 times y sub 2. And that was from the previous homework, where we worked out that the general solution for every second order linear differential equation is going to have this form right here. So the only other thing that you would need to do really would be to calculate the Wronskian. So this summarizes things. So make sure, if you use the formula, make sure you get a leading coefficient of 1. That's the only thing you have to do first. In this homework assignment, you're not going to need to do that because you don't get to use the formula. But if you do use the formula in the future, we need a leading coefficient of 1 in this position, because that's the situation under which the formula was developed. And the other thing that we would need to do is take this and y sub 1 and calculate the Wronskian, and demonstrate that it's not equal to 0, so that we know that y sub 1 and y sub 2 are linearly independent. But I'm too lazy to do that. Here's the solution for your second. This is your second solution, given that you know a first solution exists.